about short distance inverse square law tests, and you know, the inverse square law was discovered by Newton, and he discovered it by trying to understand the force on the moon in terms of the force on a falling apple, and he needed the inverse square law to make those work out. But it wasn't understood by physicists, really, but by Immanuel Kant, that the inverse square law was really just a consequence of living in 3 space dimensions. But now that there's discussion of possibly more space dimensions, this topic has had fresh interest. So the equivalence principle comes from an experimental point of view in 2 forms. There's what we call the weak equivalence principle, and that's a statement that any ordinary laboratory object will feel precisely the same gravitational acceleration if it's sufficiently small that we can forget about the tidal forces. The strong equivalence principle is, first of all, the weak equivalence principle is satisfied by any metric theory. Okay? But quantum theories of gravity may well allow some violation there. The strong equivalence principle is quite interesting. Now we've extended it to objects so large that their gravitational self-energy cannot be neglected. And then what we're studying is the nonlinear nature of gravitation. And it's interesting that it's possible to make metric theories that violate the strong equivalence principle. This was pointed out by Adelberger, as far as I know. Quantum gravity models certainly do allow for violation. Now there are 2 ways to test gravity. The obvious way is to watch things fall down. It's obvious, it's got a long history, and it's now revived again, both in experiments in space, which I'll mention, and with atom interferometers. The second way to study gravity is to watch things fall sideways, and I'll explain to you in a second what that means. This really goes back to Laurent von Etwisch. It's not so obvious, but it currently provides easily the most sensitive test of principle equivalence. So here's a brief history of the test of equivalence principle. Galileo is alleged to have dropped things from the Leaning Tower of Pisa, and the question is, are the fall times equal? And we think about this in Newtonian terms. We think there's one kind of mass that gives you inertia, and F equals ma. We call that the inertial mass. And then there's another kind of mass which is responsible for gravitation in Newton's law of gravity. And the ratio of inertial to gravitational masses in this sort of classical way of thinking about it is what the principle of equivalence says, that ratio is universal constant. Okay? We can say those 2 things are the same. Galileo did it, let's say, about the precision of 10% or so. I don't know. But he actually was a little clever. He watched things roll down inclined planes and so on. The second method is what we call the Newton-Bessel test. It's you make 2 pendulums with the same length, and you ask are their periods identical. And Newton actually did this. Newton realized he was using mass for 2 different purposes. Okay? And he actually set up an experiment where he had different materials inside little wooden boxes on pendulums, and convinced himself that those 2 masses were identical. The Etwisch test is, suppose we're sitting on a rotating Earth and we hang a pendulum. It doesn't fall towards, it doesn't hang towards the center of the Earth. Because the Earth's rotating, there's an inertial force pointing outward, and so a pendulum hangs slightly towards the equator from the center of the Earth. That angle is actually quite small, about 1/10 of a degree. And the remarkable thing is that you can compare this angle with the angle for different materials to a few parts in 10 to the 13. Now, of course, that's not how you do it. Okay? How you actually do it is you could think of schematically in this cartoon is you hang 2 different pendulums made of different materials, okay, from a rigid bar, and then you suspend that rigid bar from a very weak torsional spring. And if down is not a unique direction, in other words, if the principle of equivalence is violated, down is not a unique direction. Those two materials will hang at different angles. That will cause the bar to twist so that the two pendulums now hang straight down again. And so you see the beam only twists if the force vectors are not parallel. It has nothing to do with how long the pendulum are or how symmetrically they're placed on this bar or how equal those masses are. That's why you can do this so very precisely. And this picture shows where we assume the inertial to gravitational mass of the, I'm colorblind, but I'll call this red and I'll call that blue. Okay? The red object is bigger than the blue object, so it feels more inertial force, and so if this is towards the equator. What you will see when you do this experiment, what you have to do is attach the fiber up here, see how these hang, watch how it twists, and then to actually have a meaningful signal, you have to carefully rotate the apparatus around this wire here, this very fine wire, by 180 degrees, and then the twist will be in the opposite direction. And it's the change in the twist as you rotate the instrument that is a signal for the violation of the weak equivalence principle. Unfortunately, it's also possible that if these two pendulums, one hangs lower than the other, and the gravity field is not uniform, you will see that too. And this, so this little cartoon illustrates two things: why you can do it so precisely, and also what the major problem is. You've got to deal with gravity gradients. So a brief history of the 20th century of this. In the 1920s, Equivalence watched things falling in the Earth's field, had to turn his balance manually. In the 50s and 60s, Bob Dickey and later Vladimir Berdinsky watched things falling towards the sun. They had the idea, you know, if you're making a very sensitive thing, and now you have to turn it around to get a signal, that's sort of counterproductive because you're going to disturb it in this turning around. So they said, just leave the apparatus fixed here on the Earth, let the Earth turn in the field of the sun, and you pay about a factor of 3 in the size of the effect, but you get your instrument rotated for free. Unfortunately, your signal now is once per day. That's a very lousy frequency for an experimenter. Okay? The only frequency you can think of that's worse would probably be once a year. And starting in the 1980s, at the University of Washington, we started watching things fall in the fields of the Earth, the Sun, the galaxy, and the rest frame defined by the CMB, by putting our balances on high-performance turntables. This allowed us to have the signal at a frequency of our choosing, and not these terrible frequencies like once a day. So this shows Edelberger's instrument. He had one test body here, another test body over there. There's his fine fiber, and he had a telescope where he could look at the thing, and so he had to move over here and peer at it, and then rotate the instrument by 180 degrees and peer at it again. And you can see that this actually is not the way you would like to build an instrument to test the principle of equivalence. It's because Equivalence was concerned with money. Okay? And he developed this instrument to study gravity gradients. Gravity gradients are a sign that there's something heavy in the Earth. Okay? Something heavy is typically valuable. Okay? And what his remarkable accomplishment was, this thing, which isn't even designed particularly correctly, so to speak, was able to immediately improve the state of the art by, 4 orders of magnitude or something. So it was a brilliant idea, and he claimed that did a whole bunch of different materials with weird names, all fell with accelerations that were identical to 5 parts in 10 to the 9th with this. Dickey, back in the 50s, used all of his clever tricks where he had compared aluminum and gold, or platinum at different times, falling toward the sun. So here you see his little platinum test body, his much bigger aluminum test bodies, and the platinum body, or the gold body, is in the field of an electrical capacitor. He shined a light that reflected off these bars, and then, as Ray Rice said, he fed back to keep the balance untwisted. And he did about 280 times better than Bush. And he was frankly surprised. You know, here, this is all this clever technology, and he only improved it by a factor of 280, and he was frankly, and I know, in fact, he didn't really think that was could have possibly. He was a gentleman. He just pointed out, you know, that Equivalence himself, at this point in his life, was sort of a corpulent man, and when he stood by that little telescope, his own gravity gradient would have been a big problem. So there are two ways to think about weak equivalence principle tests. The classical way is the Newton way. Is mg the same thing as mi? Okay, that's the standard way. But in the 80s, Ephraim Fishbach popularized a new way to think about it. It's a broad gauge way to search for ultra-feeble, long-range quantum exchange forces that may lie hidden underneath normal gravity. And here's how it happened. Fishbach went back, looked at Equish's data, and you can see here on the different materials, he compared their acceleration. If they were identical, it would lie up here. And you see there was this about 5 parts in 10 to the 9th spread in these things. That's how Equish got his final result. But Fishbach noticed that if you drew a line through here and you plotted it against the quantity that Equish's time was not really known, what's plotted here is the number of baryons per gram in the different materials. And because of nuclear binding energy primarily, the number of baryons per gram of different materials varies by up to a few parts in 1,000. And there was this strong correlation. Okay? It was claimed by Fishbach that this was evidence for a new fifth force, or some interaction that coupled the baryons. It was very weak. It had a range somewhere between 30 meters and 1,000 meters. And because this new force, which has a Yukawa-type term on it, lambda is much smaller than the distance to the sun, could not be seen by any of these beautiful experiments using the sun. And that's what got us started. We very shortly showed that this was not a real thing in nature, but it got us started because the point that was raised, the larger point, I mean, this particular thing was wrong, but the larger point that this is actually a powerful way to look for new physics was right. So if we think about it now, how do we parameterize the possible departure from the principle of equivalence? Gravity couples to mass, quantum exchange force is coupled to some kind of a charge. Okay? And this charge is analogous to electrical charge, but it's more general. Okay? So there's a parameter, the range of the new force, that has to do with the inverse of the mass of the exchange particle. There is the strength of this force compared to gravity. And then there is a parameter which we introduced, which specifies in a general way the possible charge of Q, the form of the charge. We noted that this charge we can think of as an object is built up of a certain amount of hydrogen and a certain amount of neutrons, plus some binding energy of the two. Okay? And so this parameter psi expresses the ratio of the charge of hydrogen to the charge of a neutron. So there are 3 things that you have to think about: the possible range, the possible strength of the interaction, and the possible charge that's involved. And so we set up a group then called WASH, because we're in Washington, the state of Washington, and we're supported by the NSF, which we're grateful. Suppose you don't have any preconceptions about what it is that could violate the principle of equivalence. Then what should you have? Well, you should have a sensitivity to as wide a range of possible charges. Okay? And because the charge of any object or the differential charge of any dipole vanishes for some value of this parameter psi, you need to have 2 test body pairs, and you need to have 2 attractors so that you just didn't accidentally look at something which happened to be small. Okay? And to have a wide sensitivity to a wide range of length scales, you can't use the sun as an attractor because you can't see anything with a range less than an astronomical unit. And and actually the range could be anything. Okay? And so you need a site with interesting topology. If you're in the middle of a very flat place, then if there's a new interaction with a relatively short range, okay, the pendulums will fall just perpendicular to the surface, no matter what it is. Okay? So you want to be at some dramatic place in the topology, like at the bottom of a big cliff or at the top of this big cliff. And so we thought, where's the best place to go? Oh, Grand Canyon. That's a big hole in the earth. Okay? So we went to the Grand Canyon, and there is a spectacular topology site there, but it's a pretty lousy place to do an experiment. Fortunately, in our university campus, we're going to have a lab carved out of the hillside beside the deep lake, and although it's nowhere near as spectacular as this, it's actually practical. The rangers also told us we couldn't do our gravity experiment there because there could be people down here and we were dropping things. We said, no, no, we're not dropping things. And he says, you can't fool me. I know you're studying gravity. So this is the pendulum of our most recent published test. Okay? This hangs from about 1 meter long fiber. The object is smaller than a fist. There are 8 test bodies here, these barrel-shaped things. Okay? 4 of them are one material, 4 of them are the other. These are mirrors from which we shine light to detect the twist. Okay? This object here is just to protect the thing in case there's a small earthquake and it breaks the fiber, so things don't break. Okay? And this looks very bizarre, this shape, okay? But if your eyes were sensitive to mass instead of color and other things like that, this thing would, in principle, ideally, it would look like a sphere through the 6th multiple order. So this is very insensitive to the gravity gradients. And, here's some properties. It's very carefully made. Everything's gold-coated. The free resonance of this thing is about 1 millihertz. Very important is what you hang this thing from. So this is a very high-performance turntable, and we rotate the turntable at a frequency which is, just a little below the free resonance of the torsion pendulum. And it sits on feet that keep it level. There's a lot of complicated technology here. The advantage is that it allows you to boost your signal up to a high frequency, but the disadvantage is that turntable has to be very good, very smooth. It has to rotate exactly about the fiber axis and all that. Earlier I told you that these things don't matter, but in the real world they actually do matter at some complicated level. And first thing you do is you have to try to make the gravity field in which this thing sits as uniform as possible. So we have these, we replace that science pendulum with these gradiometer pendulums where you can put little tiny spheres in these carefully positioned holes. And depending how you put the spheres in, when you turn this, you measure different multiple components of the gravity gradient. Once you know what they are, you can put up some, here's an example of some of the data there, measuring the gravity gradient. What's plotted here is time, and there is one complete oscillation. So these little dashed lines separate 2 complete oscillations of the instrument. You fit this thing, extract the harmonic amplitudes, okay, and deduce what is the gravity gradient, and then you put up mass that cancels that gradient. It cancels it only right there, but that's where you care about. And you can rotate these compensators to double the gradient or to cancel it and so on. But you can only do this so well. Okay? You can do it just right, very carefully, and then do your experiment. And the first time we did it, that's exactly what happened, and this was data taken with the previous version. And then when it was all over, I asked the graders, so let's check that how the gradient cancellations are still good. And the first point, we put the gradiometer back in, and the first point was outward, but then the point steadily started changing right in front of our eyes, And this is because these data were taken in November, and November is when the rains start in Seattle. So it's the rain soaking into the ground, changing the gradient. But we can't stop the weather, but we can tune away the residual gravity moments. You see those little screws on that picture. There are 8 little tiny screws here. And what you have to do is reverse the compensators so they exaggerate the gradient, and then make your instrument insensitive to it. That's a very tricky process. It requires a patient grad student with good hands. And this shows what you see. This is a power spectrum of the twist signal in the rotating frame. This is the free resonance of the torsion pendulum. Q is about 6,000. Here is the signal at the rotation frequency. It looks like the principle of equivalence is violated. But you also notice there's something at twice, 3, 4, and so on. That's because this turntable isn't good enough. Okay. So what we do is every day we reverse the composition dipole by 180 degrees in the rotating instrument. If the turntable is not perfect, it will not change the phase of the signal if it's just due to turntable imperfections. But if it's a principle of equivalence violation, the phase should change by 180 degrees. And this shows some of the data with titanium, beryllium test bodies. And then over here we've interchanged the test bodies on the pendulum body itself. And the final result is the difference between these two averages. That's something pointing north, and these two averages, that's something pointing in the west direction. So each point is about 2 weeks of data. And the acceleration differences that we observe in femtometers per second squared are plotted here. You see that the uncertainties are a few femtometers per second squared. We can watch things in a laboratory frame falling towards the north, toward the west. We can watch things falling towards the sun. We can watch things falling toward the center of our galaxy. That's interesting because our galaxy contains dark matter. And so we're in effect able to watch things falling towards the dark matter and see if the acceleration of laboratory objects towards dark matter obeys the principle of equivalence. If it does, we say gravity. That's just what you expect. Gravity, dark matter has only gravitational interactions. That's what sane people assume. But here you have a way to actually test it in the lab. Okay? If there's some non-gravitational thing there, it will violate the principle of equivalence. The principle of equivalence is a very special feature of gravity. So what's plotted here, based on those results, this is a log scale of the range of the interaction. Here it is the astronomical unit up here. Okay. And what's plotted here is on a log scale that parameter which I called alpha tilde, which is the dimensionless strength compared to gravity. Okay. And all the results labeled EW are from our group. And as a function of the range of the interaction, the constraints get very good once you get bigger than the radius of the Earth. Okay? Here is Dickey's result. Here is the lunar laser ranging equivalence principle test. This plot right here is assume that the charge is baryon number minus lepton number. That's an interesting thing because grand unified theories have conserved B minus L. Okay, so maybe B minus L, is a global symmetry, would have its own special kind of photon. But that's strong constraints. But you see the general trend here is as the range gets shorter and shorter, the constraints get bigger, and that's for an obvious reason. As the range gets shorter, less and less matter is available to be felt by this new force, and hence your constraints are less strong. What's plotted on this axis, we pick the the charge, no, I'm sorry, we vary what we assume the charge is through its entire range here. And you see, because we had attractors to both the Earth and the Sun, there is no place where there is a zero in the sensitivity, as opposed to, say, Rogensky experiment, there were two places where there's a zero, one place where the detector Fisher dipole has a vanishing charge, and one place where the source is a vanishing charge. So this is what I mentioned, what we can say about dark matter. Here's an edge-on view of our galaxy. Out there is the University of Washington, and it's accelerating with about 2 × 10⁻⁸ centimeter per second squared towards the center of our galaxy. And although 90% of the galactic mass is thought to be dark, most of it lies outside our radius, and so it's estimated that roughly a quarter or so of the total acceleration toward the center of our galaxy is due to the dark matter. And that acceleration is still big compared to our resolution. Okay? So we can make a test. Does ordinary matter fall towards this dark matter acceleration? How precisely can we do it? It's actually pretty good. Okay? And here we say, what is the possible non-gravitational component of our acceleration of hydrogen here? Or let's say for anything towards the galactic dark matter. And you see, at the worst case, several percent of that acceleration could be anomalous, i.e. non-gravitational. There's no reason to think that it is, but we have a very decent bound. Now, a lot of people think that antimatter is very mysterious gravitation. Okay? There are meetings on this stuff. Okay? And people suggest antimatter could fall up with acceleration minus g. Okay? That's a nutty idea. Okay? And they want to do this by dropping antihydrogen, which is a very difficult experiment indeed. Okay? But let's see how plausible is that scenario. Suppose antimatter did fall up. I mean, Einstein says it doesn't, but let's just suppose it does. Okay? Photons, which are their own antiparticles, shouldn't fall at all, right? Well, we know they do. Okay? Even worse, nucleons, 99% of the mass of a nucleon is glue, equal amounts of matter and antimatter. Okay? So electrons, on the other hand, are all matter. Okay? So, protons or neutrons ought to fall with 1% the acceleration of electrons. I mean, it's nutty. Okay? Okay. But so I don't understand why they get so excited about it, okay? But, we can actually put some kind of bound on this. We can say, okay, suppose you drop hydrogen and antihydrogen. In our notation, that has a delta Z over mu of 2, +1 minus 1. Okay. Well, our test bodies have a much smaller difference in Z over mu. On the other hand, it's a much more trivial and sensitive experiment to do. So you could just say, okay, at our site, suppose you drop hydrogen, antihydrogen, and we do our usual stuff, and all we assume is CPT invariance, and we assume that there's no exact cancellation of some new vector interaction and some new scalar interaction, and then, we can set very tight bounds on how different the acceleration of antihydrogen can be. So this is a commercial, but I don't understand the speculations. Another thing you can do is, we did an experiment to complement the lunar laser ranging test, which was mentioned yesterday, watching the Earth and the Moon fall towards the Sun. Okay? That's currently the most sensitive test for does gravitational binding energy fall at the right rate. Okay? But it turns out that the Earth and the Moon test bodies differ in their fractional contribution of gravitational self-energy, which in the case of the Earth is about 500 billion, much smaller than the Moon. But the Earth and the Moon also have different compositions. Most of the mantle of the Earth and the Moon have very similar chemical compositions, but the core of the Earth, massive core of the Earth, is iron type stuff. So we made some little test bodies. One of them was like the Earth's core, iron kind of stuff, and one was built up of silicon and magnesium and so on, like the Earth's crust. And we watched them fall towards the Sun. And we saw no significant difference. And from the lack of a significant difference between these two, we can infer what that same effect would have over here, the composition effect. And when you combine those to make what we call a loophole-free test of the strong equivalence principle, you find that that is good to the loophole, subtracting our result from the related ranging. The strong equivalence principle has been tested to about 6 parts in 10 to the 4. Okay, these show those Earth-Moon test bodies, we call them, with some different kind of pendulum and so on. In April, a French-German collaboration is going to launch a satellite called Microscope into orbit, and they're going to have a test of the weak equivalence principle. And it's a Galileo test, so the detector consists of a big outer platinum cylinder, titanium cylinder, with a denser platinum cylinder inside. Okay? And in one mode of operation, this thing, orientation of the satellite stays fixed as it goes around the Earth. And you can see that what's going to happen if the acceleration of platinum and titanium differ, that this test body is going to be slid that way over here. It's going to be pulled down, but it's not going to slide over here. It's going to be pulled inward over there, and so on. So it's using a Galileo technique here, and it's in space, and so now the gravity gradients are much more benign. Okay? And the gravity gradients were actually what really limited us in the end. Okay? So here, you're going to go into a much more benign environment, and they also have a mode. It's like in our case, on a turntable, so to speak. You can make this thing rotate as it goes around, which boosts your signal frequency, which is also probably a very good thing. I think there's little doubt that these people will be able to reach their goal of 10 to the 15, because it's a Galileo experiment. That means their effect is 1,000 times bigger. Now, they still won't be able to tell you about things with ranges down to meters. Okay, they're flying 600 kilometers above the Earth, but I fully believe that this is going to be a beautiful and successful experiment. Now I want to switch gears and talk about the tests of the inverse square law. Why do it? Okay. Well, one reason is it's a completely untested regime regarding what does gravity do. I mean, we know that E and M works down to 10 to the minus 17 centimeters or so from colliders, and gravity, when we started this, wasn't known that the inverse square law worked much below a millimeter. It's obvious why we didn't know it, because suppose I think there's something with a range of a millimeter, and I make the flattest surface I can, and make it as level as I can. I put 2 little balls, spherical as I can make them, and set them on that surface. And do I expect to see them go plunk? Well, if you do, you're not an experimentalist. Okay. Another thing is, following the spirit of Planck, there is a new kind of length scale you can think of, based on the measured dark energy density, which in the units I like is about 4 keV per cubic centimeter. As far as we know, it's constant. It may not be, but as far as we know, it is. Suppose it is. And then you can get a length scale out of that, and that's 85 microns, which nobody could have told you anything about. And maybe it's interesting. There are people, well, we actually got started when we heard these stories. People tried to explain why is gravity so weak compared to everything else, and they said, but if some of these extra dimensions of string theory were large, maybe that could do it. Right? And that sounded like a nice story, and motivated us to try an experiment. And since then, there are a lot of other reasons for doing it. And one of the ones that's I'll mention is some clever idea that theorists dreamt up to frustrate experimenters. String theory is full of all these very low mass, gravitationally coupled scalar particles for which there is no evidence. you know, best of critical equivalence, inverse square law, they all work. There's no sign of anything new, but there are all these, you know, particles that people would like to have. And what they noticed was that if these have certain kinds of self-interacting properties, it could be that they are rendered invisible, and I will come back to that in a minute. So what actually got us started was this picture where it explains gravity's weakness. It's not actually weak, it's just that most of its strength has gone off into these extra dimensions where we can't go, but only gravity can go. And so the picture is, here is, you know, an open string has charges on the end, it's tightly stuck to this brane, and everything, quarks, electrons, gauge, bosons, and so on, everything but gravity is this kind of a little string. Gravity alone is a closed string, and it can feel all the volume. And if this volume out here, what's called the bulk, is big enough, then you can naturally, in this nice cartoon here, explain why gravity is so weak. Okay? And there's a little picture here I like, I got from Salvas Dimopoulos. We put a point charge down on one of our dimensions. You know, you always have to have some kind of a reduced dimensionality cartoon to show things. So here's one of our dimensions, and here's one of the curled up dimensions. So we stick a point charge down here, and we ask, what do the lines of force from this point charge do? Remember, we have to live here. And you see, in close, the distance from, we put a second point charge here, we're seeing these lines of force spread in two dimensions. It would be a 1 over r force law. And as you get out here, the lines of force have now become parallel. You're seeing Gauss's law in one dimension. It's a constant force. So it shows how testing the inverse square law is testing in a very real, direct way the geometry. And that's an appealing notion. So to see the true strength of gravity, you have to get really close. These chameleons that I mentioned have the property that in the field of matter, and normally massless, say scalar particle, for example, acquires an effective mass that gives it the property that only the outer skin of a test body is effective in sourcing or responding to the scalar field. Inside it is acquired effective mass, which prevents you from seeing it. And for example, if you have a density of 10 grams per square centimeter and natural values for the chameleon couplings, the skin thickness is only 60 micrometers. And so all these experiments you did, you know, with centimeter-sized objects, and you drew conclusions about it, you know, guys say, well, you're wasting my time, you couldn't have seen it. So here is, as of 2000, what we knew about the inverse square law. What's plotted here now is not alpha tilde, but alpha. This is something we say the true law of gravity is Newton's law plus alpha times the Yukawa factor. Okay? Got nothing to do with the composition, particularly just the masses. And you see, it's very precise when you're doing laser ranging to the moon and so on. And as you go down and down, the experiments again get less and less sensitive for obvious reasons. And now we're interested in what's happening over here someplace. And so I just wanted to show you how this experiment was done. It was done at UC Irvine by Raleigh Newman's group, and a small cylinder was suspended from one arm of a torsion pendulum inside a long cylindrical shell. Okay? And if this shell were infinitely long, it's clear that this little cylinder could not feel a gravitational force inside if the inverse square law holds. Okay? So the cylinder is moved around, and you see that it does not put a force on that little sphere, cylinder inside. And this shows the most recent published version of the instrument we developed to test inverse square law. Okay? So instead of using cylindrical geometry, we're using essentially plane geometry. Now that's good because you get more mass close together. Okay? So you have a pendulum, and its active area, its test body, is this plate here that has 42 holes and 2 ranks of 21 around it. Okay? And it sits on top of an attractor which has the same kind of a hole pattern, but it rotates uniformly underneath. And if there weren't any holes in the pendulum here, as this thing turned underneath, it couldn't exert on the pendulum by symmetry, any form of torque on the pendulum. Okay? But because of these holes, when this thing turns underneath, you would see a torque that varied 21 times per revolution of this thing, back and forth. And so that we would improve our sensitivity without being troubled by getting the scale factor exactly right, we put a second plate below this rotating attractor that had the same kind of hole pattern, except that this material was denser than the upper one, and the holes were bigger and it's thicker. And the holes in the bottom ones are just halfway in between the holes here. And so it was engineered so that if Newton's right, okay, the torque on this pendulum at 21 times the rotation frequency of the attractor, we call that the 21 omega torque. Okay? The 21 omega torque on this pendulum, due to the upper part of the rotating attractor, is exactly equal and opposite to the torque, 21 omega torque, from the lower part of the rotating attractor. So now the Newtonian signal has been greatly cancelled. But the cancellation can't be perfect. It's perfect at one particular separation. But what we're going to do is vary the separation by wasting this moving attachment of this fiber up and down. So we're measuring the signal as a function of the separation. Not shown here is a very important thing. The very important thing is a very tightly stretched, thin conducting foil. Because if you just did this experiment and thought you were going to look at gravity, you're kidding yourself. So what we do is that this, everything's coated with gold, of course, and sitting, and so the pendulum is sitting, doesn't see this attractor, it sees a golden mirror down here. It's inside the golden house. And so we try to arrange it so the pendulum has no way to know what that attractor is doing except for gravity. I will tell you a brief story. Many years ago, I was in a Fachbeirat in the Society for nuclear physics. And I made a comment because I was, from a poor country. I was from the U.S. And here was the Max Planck Society with these wonderful labs. And I made a comment about gold-plated laboratories. I have never been able to live that down. Here is a picture of our apparatus. And you'll notice it is gold-plated. And so I showed this to a famous physicist whose name I mentioned. And he says, aha, you have a gold-plated laboratory too. Now, there is less than a gram of gold in all this, but at any rate. Okay, so there you see it. Again, this thing is about 7 centimeters in diameter. Here are the holes, and what you're seeing below is the tightly stretched foil, and the golden house has been removed. And here's what you see. This is plotting one complete revolution of the attractor. And what you see here is predominantly the free oscillation of the torsion pendulum with an amplitude which is roughly thermal. So all these experiments, we are at thermal noise. Okay? And to see the effect of gravity, we put a digital filter on this that zeroes out the free torsion period. It's a notch against the free torsion period. So here's the scale goes from plus 10 to minus 10 microradians, and here it goes from a minus 0.1 to 1, so it's 100 times more blown up. And now you can see the effect of this 21 omega signal to the gravity. Okay. And we did a bunch of experiments, varying things just to make sure we were right. And this shows the results of the third experiment. What's plotted here is the torque that we measure at 21 omega and its first harmonic at 42 omega and so on. Okay. And you see that that 21 omega torque actually goes to 0. Like that's when the engineering was right. Okay. But it can't be right if you're getting closer. The fact, less than this magic distance, the fact that the upper part of the attractor is closer than the lower one is, and in fact the greater one distance is the fact that the mass of the lower one is bigger than the upper one. plotted here is when you run just with the lower plate or just with the upper plate, and that's been divided by 20. So it shows you how big the cancellation in Newtonian gravity is. But it's there, we measure it, you've got to get it right. And this shows the residuals of the Newtonian fit to the 21 omega signal. And the log scale here changes at this point. That's what the dashed line shows. And you see there are a whole bunch of points, and at the very short distances, there may be something there. But we don't throw any points away, and we analyze everything. And this shows you what you would see were there an interaction of gravitational strength with a range which is roughly, the magic 85 microns. And there's really not much evidence for anything like that. These results were taken by people at Princeton, other places, to restrain the chameleon ideas. And what's plotted here is the matter coupling of the chameleon, in units of the Planck mass, and the mass of the chameleon in normal units. And that experimenter ruled out the natural value of this coupling is somewhere around here. Ruled out a big part of the range of the allowed chameleon parameters, which is nice because it's a frustrating thing to do very careful experiments and be told, yeah, but they don't test anything. And we can also conclude, we say that a larger section dimension has a radius bigger than 44 micrometers. The dilaton is like the scalar partner of the graviton, and it's there in string theory. The dilaton can't be massless because that would screw up the tests of the equivalence principle. But we say the mass has to be greater than at least 3.5 milli-eV, or it would have screwed up our test of the inverse square law. Other people, of course, are doing these experiments, similar experiments as well. At Stanford University, the Kapitolnik group is using the methods that condensed matter people typically use with cantilevers. So you have a cantilever whose force constant is numerically roughly the same as our torsion fibers. A little tiny, but this is a microscopic thing. And you have a fiber interferometer looking at the little gold test mass. There it is actually in the real world on the cantilever. Okay? And then they move underneath a silicon nitride, silicon thing with a gold meander pattern in it. And they see, does this little gold mass here, is it attracted differently to the gold than to the silicon? And it's done, at low temperatures to get the noise down. Very high Q, and this thing would be higher if you didn't have stuff glued onto it. And in their case, the free resonance is not millihertz like ours, but it's 300 hertz because it's so much smaller. And what you see, that their statistical error is just as, is dominated by thermal noise in the cantilever. And this shows their spectrum of thermal noise. And they can't see gravity. They can't see that it's being pulled down differently over gold or over silicon, because they can't see it pulled down at all. But what they can tell you is if there were something with a range much shorter than we were able to, because this is apparently much smaller scale, that people have proposed there could be very much stronger forces at those distances. And they can set limits on things like that. And this shows you their exclusion limits on the parameter alpha. Okay, you see at 66 microns, they can exclude things 150 times stronger than gravity. But it gets worse, of course, as you get to very short distances. And there are many other experiments that people are doing, trying to test these. The thing that's our forte is we actually want to look at gravity itself. Okay. But, you know, there's really an impressive array of experiments. Our latest version of this, the next generation, we replaced that thing with 42 holes with this. This is a 50 micron thick metal foil, very thin. Okay. And it's got 120 spokes here. And it's got 18 wedges on the outside. And that sits above, that's one of these is on the pendulum, and the other is on the attractor, and the attractor rotates underneath the pendulum. And now we don't need to have a way of suppressing the Newtonian signal as clumsily as we did the first time, because the very high multipolarity of these attenuates gravity. But what you do see is, you know, if the divergence of some potential in cylindrical coordinates is zero, in other words, the inverse square law holds, if the potential varies harmonically at m, you know, 2 pi over m, okay, then the potential along the z-axis dies off like 1 over m. Okay? And so this thing is basically testing the inverse square law at 2 length scales at once. 120 spokes will have a bigger slope as you go up in Z than will the 18. Now the trick here is, this is an actual micrographical thing, but you know, we have to suspend it. So we have to glue it to something flat. And to get it actually flat enough is not trivial. But here is the simulation that Ted Cook made of the experiment. It's sped up by a factor of about 1,000. So here you see the attractor turning underneath. It's much bigger separation to actually use. That's just so you can see it here. Okay? And the signal you see, this rapid variation is the 120 omega signal. And this slow modulation is the 18 omega signal. Okay? There are 3 little spheres up here. That's because we have a turntable outside the vacuum system with 3 bigger spheres, and that provides us the gravitational optimal torque for calibration. And this shows 2 power spectra. The power in the twist signal is a function of the turntable harmonic. And you see there's a peak at 18 omega, which is visible at a separation of 1 millimeter, a separation of 40 microns. It's gotten bigger because the scale here is different. But you see, you can't even see the 120 omega when you're farther away. Okay? And it's how big this, how rapidly this 120 omega signal rises compared to that. It's a very good test for the inverse square law. So it's a cute idea. It's optimized in many ways. And here is the 120 mega signal as a function of separation, where there's a Newtonian fit and also a Newton plus Yukawa fit. Okay? And these show the residuals for Newton and residuals for Newton plus Yukawa. And there's nothing really stands out as a deviation. Okay? It all makes sense, in other words. And so, shown as a dotted line, it's a dotted line because we haven't published it, you know, officially. It's a thesis, but we're going to fix some problems that we don't know. Okay? But it's believable. Okay? So here's a factor of 10 in the vertical axis. That's nice, but you say, what does that translate in terms of range? It isn't so impressive. That's just because the signal drops so rapidly as the range gets shorter. Okay? And here's the dark energy length scale. Something happening with gravity at the dark energy length scale would be over here. That was already excluded in the 42 hole experiment, and it's more excluded. And the standard results from that experiment I showed you are plotted right there. So we rebuilt the device with flatter test bodies, smaller separation, improved vibration timing, and everything, and it's just now getting commissioned. What limits this? Well, it's really annoying. What limits it is electrostatic problems. As the pendulum, the noise is perfectly consistent with thermal until you get within about 70 microns of foil, and then it starts getting worse. And this just shows you the equilibrium angle of that torsion pendulum as a function of separation. So here the separation is now, here is 100 microns. It's starting to change a little bit. The units here are microradians, or just remember, our normal units are nanoradians. Okay? So the pendulum is being cranked around by the string theory has a landscape. We got our landscape. It's called electrostatic landscape. Okay? And so the equilibrium position depends upon the angle. This is a plot. We measure the separation capacitively as a function of time of day. And you see during normal hours, until you get to about 11 o'clock at night and starting up again early in the morning, it's quiet, but otherwise there's all this vibration. So that vibration is like moving up and down here. And that is the induced twist, you see. So we can only run at good data when the people in Seattle aren't busy driving around. And that's a problem anybody is going to experience at one level or the other when you try to do these short-range experiments. So these tests are challenging. The achieved sensitivities, are, to me at least, impressive. That differential acceleration that we resolve is comparable, for example, to the difference in little g at 2 points separated by a nanometer. So gravity gradients matter. We and many others, I haven't had a chance to talk to you, tried very hard to find some evidence that Einstein's radial theory breaks down, has some experimental sign that there's anything wrong with it. Okay? Every one of us has been unsuccessful. Okay? So the story is Einstein 4, emission of gravity waves in the pulsar, Eric Adelberger, gravitational redshift, deflectional height. Experimenter 0. In other words, we haven't found anything wrong with any of those. Okay? We can do better, and other people can do better, and we're going to do it, but you're not going to see overwhelming changes. Okay? The atom interferometer people have this fantastic instrument as an absolute accelerometer. The progress they make is really immensely impressive. But they're going to be subject to the same problems. Okay? In some ways, they're worse. We have to know what is the gradient doing right there. They have to know what's the gradient doing along a 10-meter fountain or something. Okay? So, I don't know where they're going to get, but they're going to have their own problems, which are very closely related to our problems. So Einstein, I'm sure, wouldn't be surprised if this theory works. He said if God didn't use it, too bad for God, sort of, okay? But I'm really impressed that something survived so long, and that's really one of the biggest mysteries of all. Thank you very much.